Hello, week 6. Time is passing very fast. I mean, this is even week 6 now. I just cannot believe it. It's just like we started yesterday. Whatever, we were talking about stacks and actually we talked about subroutines and how to pass parameters to subroutines. This week, we are going to start with parameter passing with stacks. You remember when we were calling a function, since this function did an operation like factorial, it needed an input and it was providing us an output. So these were called the output arguments. And how to pass those arguments. And in the previous week's slides, I told you there were 3 ways to do it. Using registers to get to provide the input and get the output out, or to use the stack. We haven't learned that, but we have learned how to use the stacks the previous week. So we'll start with how to use stacks to provide input-output arguments to functions. Then there was a third method, global variable, if you remember. Actually, global variables are using the memory, and we haven't specifically talked about the memory. This week I'm going to tell you the exact organization of the memory in our architecture, and this will help us a lot. Actually, when you're doing microprocessor-based system design or embedded programming, as an embedded programmer, you always have to know what kind of an memory organization you have. I mean, those kind of programming, embedded programming, hardware-based programming, is about touching the hardware. When you're coding, you know what you're doing in the memory. So you're writing something to the specific bits of the memory, because in a conventional or high-level programming language like Python or MATLAB, you don't know this. And in C, you don't even know this. You can get the address in C. There are operators for that. However, you don't have to. But when you're doing embedded programming, low-level C, embedded C, or microprocessors assembly, you have to. And we are going to learn. And we are going to finish with some examples. These two, some new directives and random number generator example will be the subject of the Wednesday, I guess. It will be the last hour. Okay, so we start with parameter passing. As I just summarized right now, we could do it in 3 ways: registers, stack, and global variables. We have seen registers. We are going to learn stack today. And global variables, yes, we will learn today because we are going to learn how to use the memory. Okay, so actually, it's not much different than using the registers. Because when you're calling a function from the main code, what you did was you called a function. Before you called that function, you put some variable to some specific register, R0. And if that function is using R0, you're doing it correctly. In stacks, it's just the same. I mean, you put something to the stack, and your function knows that it is at the stack. So you push the input values to the stack. How many of them, you don't care. Stack is big. Just provide them in a specific order. You call the subroutine, and the subroutine will see the inputs in, not the registers. This is wrong, guys. Very, very important. Just let me draw it. This is wrong. This should have been stack. Okay, in the stack. And then you perform your operations and you get back. Actually, I had the same table for registers, you'll remember. You know, when I was preparing the slides some time ago, years ago, I copy pasted them. I forgot to change this part most probably. Okay, so guys, we can see it. We push the inputs into the stack. We push a value to the R0. What happens in the stack? We are going to cover it. I'm going to just make my drawings again, don't worry. I call the function. Then we see the inputs in the stack corrected in the slide. So we get the values. So the first thing inside the function is I pop the values out of stack. Okay, and I push. When the last thing I do is I push the output to the stack. And when the main, so you see the input in the stack, perform the actions, then places the output in the stack. And when you're out, stack contains the output. So if you want to just use those values in your main function, you have this pop R1 so that you get the value to R1 to anywhere you like. It's at the stack. So guys, let's try to go over this example. For example, let me try to do it. So guys, this is the instruction memory. It's the instruction. It's like the instruction memory. So this line of code, imagine this is the data memory, and this is the data memory. Inside somewhere I have the stack. So I've got this. So the stack pointer is pointing to somewhere. I don't have anything yet. So I've got, and these are the registers. Let me use another color for the registers. So these are the registers, for example. This is R0, and inside R0, imagine I have 5. I mean, of course, I have it in binary, but to make things simpler for you, I'm just using 5. So guys, when I call this function, what happens is just you get this value here, and you write 5 here to the stack. And now my stack pointer is pointing to this place. Sorry. But that's how it happens, as you remember. So guys, when I call the function now, I have this value at the stack. But be careful, guys. I have taken this value from one of the registers. But this doesn't have to be the case because I'm not using the registers specifically. Imagine this was not the case. For example, I had another value at R2, for example, 7. And before I called the function, imagine instead of R2, R0, I used R2. Then in that case, what would have happened is I would have 7 here when I called this function. Why am I making a point like this? Because the factorial function will not care which register it is. It's going to take the values from the stack. So what push does is it gets the value inside the register written inside and writes it to the stack. So from which register you get it, it doesn't matter to you. Okay, let's continue. So
hocam bir şey sorabilir miyim? Bu R0, R2'dan falan alırken register'da o sayılar hala duruyor değil mi?
Yes. Tamam. When you read something from somewhere, for example, str or move or you never lose the original location's value. Okay.
Tamamdır hocam.
Good question. So I jump to factorial. The first thing I do is pop, which means I get the value inside the stack. So this is writing into R0. So the value of R0 is not important. What do I have? In the previous example, remember, I've changed R0 to R2. And at R2, I had 7. So this is 7. So this means that I'm getting value 7 to R0. So when I do this operation, what will happen is I'm going to get this value, pop it out. So when you pop it out, the stack pointer's position does change. And inside R0, I will have 7. Why R0 now? Because this function is designed such that it uses the R0 value to calculate the factorial. Now this function will calculate 7 factorial. And when it's finished, it will have a value of 7 factorial. So at R0, R1, when the function is finished, it's going to run. And when it's finished, it will have the value of 7 factorial at R1. But the thing is, we are passing the values by stack. So the definition of this function is such that it passes its output value via stack. That's why we have a push R1 here. Okay? So what push R1 is, you just push the value inside R1 to the stack pointer. When I popped R0 out, stack pointer's position was reverted back to its initial position. So I do this again. So it's changing now. Stack pointer will point the next location now. And inside stack pointer, I'm going to write 7 factorial. Okay. And when I'm finished, I'm going to call this function. And I'm going to be getting the value inside stack to a register. It is R1 here. So it seems meaningless to you because I already have R1 here. But we don't know, we couldn't be sure because we don't know if the function used R1 to calculate the result. What we only know is this function is using the stack to get the output out. So this may not be a function that you have written, you have no idea about the function. And actually, this could have been something else. Imagine this was R3. And in that case, what would have happened is it's going to just pop the value inside. This is not the case. So let's draw it. So stack pointer is pointing this place again because we have made a pop operation. And inside R3, I have 7 factorial. So guys, actually, which registers did the function used? I don't care. What I only know is the function will get the values from the stack and knows how many values it should get. And I also know that the function will put the output values to the stack. If the output have 2 output values, that could be a multiple output function, then I would use 2 pop instructions after I call the function in the main code and get the values out. That's all I know. This is called parameter passing with stack. So if you have a function which is defined as this function is passing its parameters via stack, then this is how you do it. Because in the exam, you might have a question like, okay, design a function which does this and which does a parameter passing by stack. In that case, what I'm trying to say is this stack will be provided its input via a push operation before it's called. And the outputs will be gathered in the main code via a pop operation after it's called in the main function. Plus, inside the function will read the values via a pop operation at start. And at the end of the function, it will save its output value to the stack via a push operation. So that's actually, if you understand what stacks are and what they are, it's quite simple, but this is what it is. Any questions about parameter passing by stacks? Sorry. Any questions? No, I guess. Okay, so I continue, guys. So you see the inputs and at the outputs, stack contained outputs. Okay, now we start something more. This is called the memory, guys, and memory is something very important. Whenever we try to understand something about the architecture of the microprocessors, we look at the architectural design of the microprocessor. So that's it. We have the main processor. Inside this processor, we have the control unit and the arithmetic logic unit. You'll remember the components of the microprocessor from first week, maybe, if you don't just follow the slides, whatever. So, and we had some common components in microprocessors, which we also have in our ARM processor as well, which are called the internal peripherals, which are the registers actually. The scratch paper registers, müsvedde registers, and the special function registers as well. They are here. They are quite close to the processor, and actually they are connected to the arithmetic logic unit so that we make operations on them. Okay. We have another memory type of, because this type of memory cell, this is not called the memory, they are called the registers. They are called the internal peripherals, but they are like memory because you can keep information in them. Some registers you cannot write directly, they are flags, you read them, but some of them are scratch paper registers. You just read them. They are for you to use and to do your arithmetic operations, but they are not called memory because memory is something more general. And actually, apart from this register bank we have here, which is called internal peripherals, we have 2 types of memory elements in our architecture. The first one is the instructions flash ROM memory. The instructions are kept here. This is a flash type memory because flash type memory is when you power this memory off, you don't lose the contents of it. What I mean is you load a code inside this memory because it's the instruction memory, the codes, the instructions, your assembly language code is kept here. When you power the card, your card off, you don't lose them because that's what flash type memory is. And you don't want to, because imagine this could be your washing machine. And imagine a washing machine which forgets its program every time it's switched off. It doesn't. I mean, it's there. So you need a flash type memory for that. And flash is also reprogrammable. So flash RAM, flash ROM, these are embedded systems concepts, and there's a course next year for that. It's for 69 embedded systems. We talk about them there, but this is beyond the context of our course, but I'm just telling you just to let you know. Flash ROM is kind of a ROM that you can program not on runtime, on compile time, but it keeps its information while off. So, and we have another memory. Actually, we've discussed this because whenever we write a code, this was written inside the instruction memory. And instruction memory was like any memory. What I'm trying to say is it is composed of banks, some cells, and each cell has an address value. And actually in your code, what we call labels are some address memory locations. So when I say start and start writing codes, it means that start is an address in the instruction memory, like this. I'm just giving, imagine start is this. And at that location, I have the first line of the code. At the next location, I have the second line of the code, blah, blah. It goes on like this. Actually, we are kind of accustomed to this. We've also talked about the data memory. This is where we keep our data, not the codes, data. It's a different type of memory because it's architecturally placed somewhere else. Instructions are connected to the control unit of the microprocessor. Data is connected to the data bus and the input-output ports. You don't know what input-output ports are. We are going to learn general purpose input-output GPIO in a microprocessor in the following weeks, but the data is connected to the microprocessor and the data input-output ports, because in a microprocessor, in future, you'll see that you'll have to communicate to the outside world. So the data memory is where we keep our data. Structurally, data memory and instruction memory have no difference. Bank of cells, each of them having some values, 32-bit values, and each cell has a memory address. You remember in the first lectures of this course, I always made an analogy. A memory is like a hotel. There are many rooms there. Inside the rooms, there are people, which is information or bits. And each room has a hotel number, a room number on its door. So the addresses are the room numbers written on the wall, on the doors. And the value inside are the people staying inside. And just like the hotel room numbers, they're incremental. So you've got a number, you've got a number. But we've never talked about, okay, we have an address value and we have a cell. How much data it can keep inside? I always said that this is a 32-bit memory. So you maybe thought that this should be 32 bits. Actually, they are not. Because that's a design issue. You can design a system like that. But for our system, it's a bit different. It's a bit more complicated, which we are going to cover today. Okay, and I'm starting to cover it right now. So guys, this is the data memory, and this is what we are going to learn today. Guys, this is the 32-bit system. Because the arithmetic logic unit inside can do its operations, subtraction, addition, using 32-bit numbers. Well, you may ask, can I make 64-bit operations? For example, double, again, I'm repeating, embedded systems course, the next one, the elective course, talk about these concepts very in detail. However, this is beyond the scope of this course, but in C language, for example, in MATLAB also, in Python also, you have specific data types like double. You are keeping a floating number, a decimal number in double, A equals 3.9. You have a specific way of keeping that data in the memory, and that data is actually 64 bytes, because double universally is defined as 64 bytes. So can this microprocessor make 64 bytes of operation? Well, it can, but it's not that easy. it doesn't use a single instruction. For example, imagine you write a code in C, and actually when you compile the code, it's being converted to assembly. And in assembly, that code is maybe summing up to doubles. Most probably in the assembly, you are using many instructions together. What I've been talking about in this 1 minute is beyond the scope of this course. In the scope of this course, we will make instructions using only the assembly language. Mul s, multiply, adds, subs, the instruction that you've learned so far, assembly instructions. Those are 32-bit instructions. They make operations on 32-bit numbers. That's why they call the system as a 32-bit number. However, a big but, the memory is composed of 8-bit cells, guys. Very important. I need everybody's attention here. In our architecture, some other architecture might be different, but in Cortex-4, this is the basic architecture of ARM M4 Cortex M4 architectures, because this is the basic and most fundamental architecture of mobile systems ARM use. We have a memory bank. Each memory cell has an 32-bit address value. Careful. The hotel room number written over the door is 32 bits. This guy is 32 bits, okay? This is the room number. This is the room number, guys. Room number, okay? It is written over the door. But the rooms are 8 bits. Room number, 32-bit. Sorry. 32 bits. But the rooms are 8 bits. I make the same analogy. It's a stupid analogy, but I hope it works for you. We have a hotel. We have hotel rooms. The rooms are 8 bits of size. So if you're 8 bits wide, you can fit. If you're larger, you need more than one room. But you need your numbers, I mean, because in a computer, everything is numbers. The residents of the hotel are numbers. So if you want to stay inside a room, you have to be at most 8-bit. If you're 16-bit, you will need 2 rooms. However, the room numbers written on the door are 32 bits. What I'm trying to say is, imagine this is a room number. The next room number, I'm increasing this number, this is an hexadecimal number, base 16, by 1. This is another room. They both have 8-bit values. Be careful, this is an hexadecimal number with 2 nibbles. This is a nibble, that's a nibble, because this is 4A, so 4A is an hexadecimal number. And in binary, what is this? This is in binary, this is 4, and this is A. So this is the number. So in this hotel room, I have this binary number. Very important. The memory is composed of 8 bits, 2 nibbles, 2 X's. Each 8-bit part has a distinct memory address. This is the address. So each adjacent address carry 8-bit values. Each adjacent address carry only 8-bit values. Any questions about this? Because everything what we're going to be talking about in future will be based on this. Any questions? No, guys, it's simple if you understand it clearly. Okay.
Hocam,
so, please.
Tam olarak hangileri 8 bit, hangileri 16 bit olduğunda 2 oda demiştiniz. Bu nasıl oluyor? Tekrar anlatır mısınız?
Well, there's one fact that never changes. The memory, our hotel, is composed of hotel rooms. Everything is 8 bits. There are no 16 bits rooms. Okay? Everything is 8 bits. So regarding your question, imagine you want to keep a 16-bit value. For example, let me write a code here. Sorry. Imagine LDR. No, let's say that this is STR. We are going to do these examples, but I'm going to be doing this for you. For example, you remember what this code does? You have a 32-bit value inside R0. You get the value inside R0, which is 32 bits. You're writing it to somewhere in the memory, which R2 points out. Imagine in R2, let me write this. So let me draw the register bank here. Imagine R0 have this value, A0, 0, 0, 0, 0, F, F. And R2 have this value, which is, let me write, I've specifically chosen to write this value, guys, be careful. So what this code does is, it gets the value inside R0 and writes it to the memory location this guy points, and this guy is pointing to this memory location. Well, R0 is 32 bits, and this memory location is only 8 bits. So if you want to write this value to the memory, it will not fit in this address only. It will be written to a total of 4 addresses, because this is 32 bits, and at each cell I have 8 bits. That's why it's going to be written into 4 cells. That was what I was trying to say. We're going to make examples on this. Okay? But don't forget, every cell is 8 bits. Nothing can change it. But if you want to write a larger value, you will need more rooms. Okay, you come to the hotel reception. You want a room. It's like STR. STR is like R0, the value inside R0 is going to the hotel reception. Okay, how many bits are you? I'm 32 bits. I'm going to be giving you 4 cells, 4 rooms, like this. We'll make clear examples and it will make it simple for you guys. So this is the address binary value. Never forget, the hotel room numbers are 32 bits, but the people inside are 8 bits. Okay, this is the data value inside the address, which is 8-bit binary value. This is the architecture for our card. This could have been the same. But learning this architecture and applying it will enable, it will help you in future if you use another type of architecture with different bit designs and bit lengths and word lengths. You will understand. But we will make our examples in this course based on this, okay? We'll never have memory cells larger than 8 bits. In this course, we'll use these cells. So guys, actually, I've used STR and addressing modes. We have to remember this. So guys, when we used LDR, we could use 3 types of addressing modes. This was LDR. Actually, this operation had nothing to do with the memory. You are saying in the code, hey, microprocessor, write this value to R0. And if you look at the architecture, that value is being directly written from here to here. Okay, so this line of code has nothing to do with the memory. This line of code also has nothing to do with the memory because you're transferring values between R0 and R1. Similarly, there's R0 inside here, and there's R0 inside there. They are written between them. However, LDR is not like that. And also STR is, using the STR is not like that as well. You're writing or reading from the memory. And you're writing actually, since these are registers, and they are registers, they are 32 bits. You're writing more than 8-bit values. So it's a bit complicated, just like I've told you, you're using 4 rooms. But which 4 room? How do I understand it? In which order I put them? These are the important questions, and we are going to cover these. Okay, so these are only values, only register names, and this is related to the memory. That's called index addressing. Actually, index addressing is the way you access the memory in a microprocessor. When you learn addressing modes, this is what it's for. And this square brackets indicates the index addressing mode. So whenever you see a square bracket, never forget that you are touching the memory. And if you don't see it, never forget that you are not touching the memory. Okay. Now, guys, let's try to make this example more in a more detailed way. Let's see this example. I tried to make an introduction, but let's go deeper into it. So this is index addressing. What I'm trying to say is, I'm going to read a value from the memory and write it to R1, right? Because that's LDR. So this means go to the 32-bit address, which is written inside R1. Be careful. Be careful, guys. I said that the address values are 32 bits. Always the room number written on the door is 32 bits. And your registers are always 32 bits. That's a wonderful match because that's a design. So inside R2, there is a value. So imagine this is inside R2. Okay. What you say is go to that location. Okay. Actually, going to a location in the memory is about pointing to that memory. I'm just going to point that memory. Okay, I'm pointing to that memory. Okay, you're going to read your value from there. Guys, now there's an important definition. LDR reads 32-bit values. So what I'm trying to say is, of course, the address is 32 bits, but it's going to read 32-bit values from the memory. That's the definition of LDR, because there is a 16-bit version of LDR as well, which is LDR half. But LDR reads 32-bit inputs. So go to that address and read 32 bits and get that value and write it to R1. Okay, there are lots of bits in the memory. I can read 32 bits for you. But you said R2, and R2 is pointing to a cell. It's a single cell. And that single cell only has 8 bits. So you want me to read 32 bits. So I guess I'm going to be reading some cells neighboring this pointed location, right? So which one? There are rules for this. I'm going to be teaching you those rules. Actually, it's going to be reading the succeeding 4 ones, including 2. So it's going to be reading these values, guys. Starting with this one. And since this operation is 32 bits, 3 cells more, which will make a total of 32 bits. So using this 32 bits, I have a value of 32 bits. And I'm going to be writing that 32 bits to R1, right? So R1's value will be a 32 bit. Good, now I get the idea. R2 is pointing to an address. Since LDR is a 32-bit instruction, I need to read 4 cells because 32 bits corresponds to 4 cells in the memory. Which 4 cells? Starting with this address, succeeding 4 cells, this one and 3 more. Okay, that's for sure. Okay, but there is another question. I've got these numbers. I'm going to be writing it to R1, but R1 is 32 bits. Which one is the most significant bit? Which one is the most less significant? Shall I write FF as the most significant one, or hexadecimal 23 as the least significant? How? There's a rule for that as well. Actually, it's called the endianness. I'm going to be showing that to you as well. Any questions about this part? Okay. I'm reading this part. Guys, there's something called the endianness. Endianness decides where to write as the most significant bit or the least significant bit. Let's read the paragraph and it will make much more sense to you. And I'm going to provide you an example. How is a 32-bit pattern held in your 4 bytes of memory? Okay, it's 32 bits, but how it's held? I mean, you're going to put it to R1. Which one is the most significant bit? Which one is the least significant bit? There are 32 bits in 4 bytes and 32 bits in pattern, but a choice has to be made about which byte of the memory gets what part of the pattern, most significant or least significant. There are 2 ways you can do this. The big endian byte order and the little endian byte order. I'm going to be continuing reading the little endian one because we are using little endian. The least significant byte of the data is placed at the byte with the lowest address. So lowest address, least significant byte. What does this mean? I was reading values from 4 memory locations. Each memory location has an address value, hotel room numbers. In little endian, the rule is this. You read the lowest address and write it to the least significant part. So guys, lowest address has 23. I'm writing 23 to the least significant part. Next one, next. Thus, the highest address is written to the most significant part. This is called the little endianness. And if you don't change the default configuration of this card, we will be using little endianness. And I'm not going to change it. In your exams and in your labs, you will always be using little endians. That's how you read this. If it was big endian, I'm going to make an exception only for once and show you what big endian is so that you could understand little endian. Our system is little endian. But if our system was big endian, so if it, sorry, it was big endian, then this code will provide R1 value of, in that case, it's the opposite. Highest address value goes to the least significant bit. So it would have been the exact opposite, like 23, 34, 45, FF. So this value written here, this value written here. But this is not our case, okay? This is big endian. We are using this case, okay? This is called little endianness, and we'll always be using this. Least significant values, least significant byte, will be taken from the lowest address if you are using multiple addresses to represent a value. Any questions about little endianness? Good. I guess it's simple. So the little endian is our default in ARM M4. That's what we'll be using in the exams. So guys, actually, we are going to do this today. You can observe the memory in Kale as well. So when you write something in the memory, you can observe those values. And actually, you can see what values you have. For example, I have done some experiments, and this is a debug mode. As you can see, I have the yellow triangle, which means I am about to execute this line of code, which I have not yet. I have not yet executed it, which means I have executed these lines of code. Let's see what these lines of code do. This is a NAT value. So in R2, I have this value. You can see this. And in R0, I have this value. Also, you can see this because I have already ran these codes, right? So what I do in str, so when I call str, R0, R2, what I do is, let's draw it. Let's do this drawing that we do all the time. You have a memory bank. Okay. And imagine this part of the memory is 200 something. So this is the part of the memory because this was the value inside R0. So str is go to R0, R2, pardon, where R2 points in the memory. It is where it points. str is a 32-bit operation. It's a 32-bit operation. Write the values, all values of R0 inside R2. We have the same problem. Which one? If it's little endian, the lowest byte will be written to the lowest memory address. So the lowest byte is this, right? It will be written to the lowest address. So this is 1. The next address will be the next byte. So this is the next address. It will be written DC. And it will be FE. Well, I always told you this is the way. So how can you test it in Kale? Actually, in Kale, you can read a part of the memory. If you open the memory tab, which I'm going to be doing in the next hour, we are going to give a break, and I'm going to be doing this on Kale. And you write your stat address in the memory. This will show the addresses of the memory. Actually, you can change this configuration. This is the way it shows only bytes, hexadecimal bytes. You can change this. We are going to do this, but don't mind it right now. It's like showing each cell. So guys, this is the first value is this address. The next value is 20001, 20002, 20003, 4. And if you count as hexadecimals, this is 20000 hexadecimal 24 and 25. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 1, 0, 1, 1, 1, 2, it goes on like this. Okay. These are the memory values. I mean, actually, there are some values here you don't see because it will not make the exact count because this is a screenshot I just cut, but there are some values here as well. Okay, so don't be fooled by that. So as you can see, guys, at 200, I have this value, just like I've here. In 201, I have this value. In 202, I have this value. And 203, I have this value. This is how you can check your little endian is actually working. And we are going to be doing this on Kale as well. Any questions? Okay. Okay, if no questions, let Zoom record it and we'll continue in the next hour. Stop records.